Hello everyone, I'm Indu Joshi. I'm a PhD student at the Computer Science Department, IIT Delhi. Today, I'm presenting the research conducted by me and my team. The research is titled Explainable Fingerprint ROI Segmentation using Monte Carlo Dropout. Fingerprint matching systems are one of the most robust biometrics-based authentication systems. These are used for various access control, civilian, and forensics application. Although fingerprint matching systems are generally quite robust, however, it is observed that fingerprint matching performance is adversely affected due to presence of background noise. Fingerprint ROI segmentation is typically the first step in fingerprint pre-processing pipeline. This step is targeted to separate the foreground fingerprint and background region. By limiting the foreground fingerprint region, ROI segmentation helps twofolds. Firstly, it reduces chances of spurious minutia detection. Secondly, it reduces computation time for performing fingerprint matching. Fingerprints can be acquired through different sensors employing disparate sensing technology and leading to varying sensor and background noise. Generalization to different backgrounds originating from disparate sensors is challenging for ROI segmentation algorithms. Approximating model uncertainty provides a means to quantify models' confidence in ROI prediction. High uncertainty indicates the possibility of erroneous predictions. In this research, we use Monte Carlo dropout to calculate model uncertainty. In this figure, the first row represents the input fingerprint image, whereas the second row represents the model uncertainty predicted by the proposed work. In the uncertainty maps, blue color denotes low uncertainty values, whereas red color denotes high uncertainty values. As shown in the first and third column, around the noisy background regions, the predicted model uncertainty is fairly high. Similarly, in the second column, in the fingerprint region with low ridge clarity, the predicted model uncertainty is high. Now we summarize the research contribution. So, most of the models proposed in the fingerprint ROI segmentation literature are not end-to-end and require post-processing. As the per pixel label might change due to post-processing, therefore, true uncertainty cannot be evaluated on them using Monte Carlo dropout. Towards this, we benchmark the performance of 4 state-of-the-art semantic segmentation models on fingerprint ROI segmentation. Having found the best performing segmentation model among the evaluated models, we modify the network architecture such that model uncertainty in segmentation is obtained. To the best of our knowledge, this is the first work to introduce model uncertainty guided explainability in the fingerprints domain. We benchmark the performance of conditional generative adversarial network, UNet, CCNet, and recurrent UNet on fingerprint ROI segmentation. Now we present the benchmarking results. To evaluate the 4 models, we use 2 different evaluation metrics, namely dice score and checkered similarity. We find that our unit outperforms all the other 3 models on both the evaluation metrics. So our unit turns out to be the most effective baseline model for fingerprint ROI segmentation. However, As RUnit is not a explainable model by design, we employ model uncertainty in network architecture of RUnit to understand its confidence in prediction. Now let's talk about how to calculate model uncertainty. For a given test input X test, to calculate the output, the Bayesian neural network requires posterior of weights given the training data. However, the posterior probability of weights is intractable for a deep neural network. Variational inference is one of the techniques to approximate the posterior. It requires defining and approximating variational distribution, and it is required to be close to the true posterior. Given a deterministic neural network, Gall and her colleagues show that by reparameterization of the approximate variational distribution as Bernoulli, it is possible to approximate variational inference from a deterministic neural network. Through Dropout, one samples binary variable for each input and for each network unit in each layer. Let yi denotes the output of layer I. Through application of Dropout, yi is equal to ri into yi, where ri denotes the probability of binary variable to take value 1 in layer I. Thus, ri is Bernoulli distributed. This demonstrates that Bayesian inference can be approximated from any deterministic neural network by incorporating Dropout in its layer. After the introduction of Dropout, this integration can be approximated by Monte Carlo integration over stochastic outputs. And then the model uncertainty can be approximated as the variance of these stochastic outputs. To approximate Bayesian inference from RUnit, Dropout is used on each convolution layer. For a test input X test, the variance of the predicted output is the model uncertainty. Next, we find that Monte Carlo dropout not just helps to quantify models' prediction, but it also works like an attention mechanism. Through these examples, we show that drUnit performs a better job in segmentation compared to RUnit. In the first and third row, we find that whole of the fingerprint image is incorrectly detected as foreground by RUnit, whereas drUnit correctly segments the foreground fingerprint. In the second row, we see that some of the background region is classified as foreground by RUnit. However, drUnit does a better job than RUnit. We also calculate Jaccard similarity and die score for both these networks and find that DRU network indeed outperforms RUnit on both the evaluation metrics. Next, we show some of the successful cases and see that the drUnit generalizes over different data sets and works for different background and sensor noise. However, we do find that if the intensity in the background is very similar to the intensity in the foreground, then drUnit sometimes makes erroneous predictions. Next, we show the uncertainty predicted by drUnit for the successful and failure cases. In the first two columns, we show failure cases of segmentation by drUnit, and the other three columns represent successful cases. In the first column, complete fingerprint image is classified as foreground, whereas in the second column, the background towards the right is classified as the foreground. We see for both these cases that higher uncertainty is predicted, especially around the regions where indeed erroneous prediction has been made. We also see that the uncertainty predicted for successful samples is fairly low. We also evaluate DR unit on 3 other metrics proposed in the literature. First one is erroneously classified patch percentage. This gives a percentage of erroneously classified 16x16 patches compared to the ground truth segmentation. We calculate hit coefficient, which indicates the relative foreground fingerprint area correctly detected by the segmentation algorithm compared to the ground truth. On the similar lines, we calculate mistake coefficient, which indicates the relative fingerprint area incorrectly detected as foreground by the segmentation algorithm compared to the ground truth. We find that DR unit achieves competitive performance compared to the state of the art on all of the 3 metrics. We also compute Jacquard similarity and die score and find that the performance of DR unit is competitive on some datasets while it outperforms state of the art on some other datasets. We argue that the better segmentation performance of state of the art algorithm compared to DR unit is due to the availability of higher number of samples for training for the state of the art, as the state of the art model is trained on a 16x16 patch. Therefore, the number of patches for training is fairly high compared to DR unit, as DR unit is an end-to-end model which works on the whole image. State of the art requires pre-processing to predict the segmented ROI, where DR unit is an end-to-end model, but it also outputs uncertainty map, which quantifies confidence in model's prediction. To conclude, experimental results and visualizations demonstrate the fact that introducing Monte Carlo dropout works like an attention mechanism and also provides models confidence in prediction. We show that proposed model correctly outputs model confidence by predicting higher uncertainty around highly noisy and incorrectly predicted fingerprint regions and low uncertainty values around regions with clear wrist structure and low background noise. In future, other methods on uncertainty quantification can be explored. We thank the HPC facility of Indria Sophia Antipolis for computational resources used in this research. I am partially supported by the Raman Sherpa Fellowship 2019. We also thank the French government and its National Research Agency for partly supporting our research. For any queries, you may write to me at the email address as shown on the screen. Thank you.